Thank you very much. Hi, thanks for having me, and thanks to the organizers once again for putting together such a great conference. Yeah, so I am an algebraist, and rumor has it that there are quite a few people here who are not algebraists, so I thought I would give a little bit of a frame of reference for the sorts of things that I think about. So I work in combinatorial representation theory, which still irritates to no end my mom because she tries to tell people what I do, and that's a mouthful. So in representation theory, what do? We look at algebraic objects, usually algebras, and we want to know things about them. We want to understand their structure, and the way we cheat to understand their structure is to study the representations. So what are the representations of an algebra A is the first question you ask. And then once you start to work with that, immediately you realize that's a terrible question, and you want to study something that you can actually get your hands on, so you study the simple or the irreducible representations. In order to classify those irreducible representations, one of the easiest things you can get at is what's the action of the center. So you classify representations by their central characters, which is just basically how does the center act. And then you want to know things about their structure. The overall action would be great, but things, statistics like what are their dimensions? If they're not irreducible, how do they decompose? Things like that. And then how can I combine old modules, or how can I take other modules and make new modules out of them? Take direct sums, tensor products, or maybe you induce up from one module to another. So take the center, take an irreducible representation for the center and induce that up. That's a good way to build modules. The combinatorial part is that we take combinatorial tools like partitions, graphs, lattices, stuff like that, in order to index representations, which is just to say you build up a bijection between all of the combinatorial objects like this and all of the irreducible representations of that thing, and then you use that combinatorial information in order to recover structural information about the representations. So I say, okay, all of the partitions of 5, the integer partitions of 5, for each one of those I get a representation of that thing, and also I know how big it is and what the action is and stuff like that by reading little things off of the integer partition. So that's what combinatorial representation theory is all about. How did it get started? Well, the motivating example came from the symmetric group. So the symmetric group, permutations, the group of permutations, but really the way that I like to think about it is with these diagrams. So set up, k dots on the bottom, k dots on the top, and draw a bijection from the bottom to the top. And I like these because, well, one reason is because when I want to multiply permutations, I can stack one on top of the other, glue the middle dots, and resolve. So multiplication given by concatenation. So this is our first example of a diagram algebra. So it's a group, but if I take the group algebra, I have an algebra. So the symmetric group, that's the very first thing you learn about when you take baby algebra class. And what do you usually do? You don't usually think about it as these diagrams, you think about it in cycle notation. And then you learn, okay, the conjugacy classes of permutations are indexed by integer partitions, right? I look at the cycle type, and I say, okay, from biggest cycle to smallest cycle, well, that's an integer partition of k. And then if you learn about representations, group representations, the very first thing you learn is that the irreducible representations are in bijection with the conjugacy classes of the group. So that means the irreducible representations of the symmetric group are indexed by integer partitions. So that's the very baby case. Well, Schur comes along and is trying to classify not just representations of finite groups like the symmetric group, but wants to classify representations of infinite groups like the general linear group. And his observation was that the general linear group, well, I at least know one representation of the general linear group. It's its favorite module, right? GLN acts on n-dimensional space, and that's a module. Okay, and I can build new ones by taking tensor products. So if I take a bunch of those n-dimensional space and I take a tensor product of it, well, the general linear group acts diagonally on that. So I can build new representations out of GLN's favorite representation. The action is diagonal. But the interesting thing about this module is that it's also invariant under permutation of the factors. So I can take those k factors and permute them using the symmetric group as k. And these actions commute. So if I first act by a matrix, and then I permute I get the same thing as if I permute and then act by the matrix. So all of my maps here are moving up. So you start down here, you act by the matrix, you permute, versus you permute and then you act by the matrix. Same thing. So these actions commute. In representation theory, that means that it's a bimodule. It's a GLN-SK bimodule. Both of them can act simultaneously because those actions commute. Even better, they are all of the things that commute. So if I look at the image of GLN inside the endomorphisms of that space, so the endomorphisms are just a bunch of matrices. If I look at the matrices that are coming from the action of GLN, then I look at what commutes with that. So this is all of the stuff that acts by GLN, and then the stuff that commutes with the symmetric group. That's it, is the stuff that came from the action of GLN, and vice versa. If I look at all of the action of the symmetric group, and I look at everything that commutes with it, that's it. That's GLN. So one is the centralizer of the other. I think I'm getting myself mixed up here. But anyhow, if you look for the stuff that commutes, that's it. And the amazing thing that does for me is it produces a matchup, a bijection, between the GLN representations appearing in this k-fold tensor product and the symmetric group representations appearing in this k-fold tensor product. Because as a bimodule, this thing decomposes with multiplicity 1. So if you've done a little bit of work in representation theory, you learn that, okay, up to isomorphism classes, so if I take all of the stuff that's mutually isomorphic and I break it up in that way, that's unique. But if I try to take the component of the sum of all of the isomorphic stuff, there's no unique way to decompose that, so it can be a little bit harder to deal with if there's more than one copy of the same thing. But here, because of these double centralizer relationships, what happens is that these all have multiplicity 1, and so it's really easy to decompose it, and you get a pairing. So you get a pairing between symmetric group modules and GLN modules inside of the space. So for example, if I take the threefold tensor product with n huge, yeah, n has to be big, then I get one that corresponds to the integer partition 3, one that corresponds to the integer partition 2 plus 1, and one that corresponds to the integer partition 1 plus 1 plus 1. Because we already knew how the symmetric group worked, right? The symmetric group, we already knew that its representations were in bijection with integer partitions. And so now we've learned that the general linear group has a bunch of representations that are indexed by integer partitions. And by varying k, by taking bigger and bigger and bigger tensor products, I'm going to generate more and more and more representations of the general linear group. And you learn, by playing this game, that the general linear group, GLN, it's an infinite group. It has an infinite number of simple representations. But they're indexed by integer partitions of 0, 1, 2, 3, 4, all the way up, all of the integers, that have no more than k parts. So that's what I was saying, is n has to be big, otherwise like these partitions get cut off. But like this has 1 part, this has 2 parts, this has 3 parts. So as long as n is bigger than 3, this is fine. But that means that the irreducible representations of GL5 are indexed by integer partitions with up to 5 parts. Okay, fantastic. You can also learn a little bit about how this tensor space breaks up by looking at starting with just one copy of Cn and starting to tensor on more and more copies. So if I take one copy of this thing, it's indexed by a box. That's, every representation of GLN is indexed by some partition. This should have C to the n, by the way. Sorry, I'm missing a C to the n. B is C to the n, all of a box. If I tensor on another one, I get 2 partitions. These were partitions indexing S2. I know that these partitions, the representations corresponding to these partitions for S2 are both one-dimensional. That duality then tells me, well, the dimension of one representation was the multiplicity of the other. So there's not just a pairing, but they also transfer representation theoretic data. Remember, things that I want to know is how does stuff decompose and what are its dimensions. So this says that inside of this space, I get one of each of the modules indexed by those things for GLN. If I tensor on another copy, I know how that decomposes as an S3 module, and so I learned how it decomposes a GLN module. I get 3 different GLN modules. Before, the dimension of the S2 module, or the S3 module, was 2-dimensional, and so I get a multiplicity 2 decomposition inside of that space, and so on. I know how to build this up in terms of the symmetric group, and so I know how to build it up in terms of GLN, and so on. Again, if I take a partition, that represents both a representation of the symmetric group for that level and GLN for any n, for big N. And if I look at the paths down to that point, those were basis vectors for the symmetric group module, and so they also become multiplicities. Each one of them gives me a representation of GLN. Fantastic. So this is what we mean by combinatorial representation theory. There's representation theoretic data. I know how things decompose. I know what they're labeled by. I can keep track of them. How big are they? Stuff like that. But also, how am I doing that? I'm doing that with combinatorial data. Integer partitions, lattices. If you've seen these things before, the paths are called Young tableau, that kind of information. Okay, combinatorial representation theory. But that was like over 100 years ago. So what's happened since then? So that phenomena, that pairing of representations, is called Schur-Weyl duality. Schur because Schur came up with it, Weyl because he wrote a very fancy book and everybody thought it was his for a while. But it's not. It's Schur's. So okay, so then Brouwer comes along. Brouwer, working off of Schur's work, says, okay, great, you did GLN. What about ON? What about SP2N? Those kinds of things. And he did the same thing, where he said, okay, if I take their favorite module and I take a k-fold tensor product of it, what endomorphisms commute with that action? And built the Brouwer algebra. The Brouwer algebra is another diagram algebra. Take k dots, do a bijection between them, except that now it doesn't have to be a bijection from the bottom to the top. It can be a bijection overall. So you can have, top to top pairings and bottom to bottom pairings. This light purple stuff is stuff I'm not going to get too much into, but the point is that this diagram is encoding a map. It takes some simple tensor on the bottom and spits out some linear combination of tensors on the top. So it's just a diagram that's encoding a map on the space, encoding an endomorphism. The only new thing about this is that you get these, with these bottom to bottom loops or the top to top loops, if I stack and try to concatenate, I might get closed loops in the middle, in which case I have to resolve those. I want to suck them into the center of the algebra. A good element, or good elements of the center, are actually just like numbers. And so you resolve those with the dimension of this space. And that gives you a commuting action. For orthogonal space, you also get one of these lattices. Again, that should be Cn. I start tensoring on. But now I get some new stuff. I get my old partitions, but I'm also can remove a box, so this is a trivial representation. So you add or remove a box. Add a box, 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 or remove a box, remove a box. And those are the rules for tensoring on taking k-fold tensor products of these things. And it generates another big old lattice. The point of this is, again, we've got partitions, we've got a lattice, you get paths in the lattice. The paths in the lattice tell you things like dimensions of the diagram algebra modules or multiplicities of the orthogonal or symplectic group modules. If I look at type A, GLN, SLN, but make that very, very small. So remember, I was looking at GLN as partitions of height no more than n. So if n is 2, right, that you lose a lot of information right away. And it turns out that the symmetric group, I mean, anytime you have an action of an algebra on a module, some of the stuff is going to act by 0. So you're going to get a nice big kernel. And the smaller the n, the bigger the kernel. And so it turns out that it's pretty worthwhile to actually look at what is the quotient of the symmetric group that still acts when you modify the kernel. And you get the Temporally Liebe algebra, which is these guys. They look kind of like Brouwer diagrams, except that they can't cross. That's the difference with the Temporally Liebe algebra. By the way, this is Brouwer algebra, Temporally Liebe algebra, okay? Temporally Liebe algebra actually comes up in physics all the time, talking about spin chains and Ising models and transfer matrices and things like that. So a lot of times, I mean, the paper that I've been thinking about most, that I'll talk about in a little bit, has been the hang up on this paper. Like, we've had the theorems for years. The trick is trying to get the physicists to agree that we've solved their problem. All right, so this paper has been draft after draft after draft handed to the physicist. Yeah, but what is this little operator in this space? Oh God, okay. All right, anyhow, that's why this has such a late date. 1971, we understood the symmetric group way back in the, 1800s. Why did it take us so long to figure out this Temporally Liebe algebra? It was actually because the physicists came along and said, oh, this models something amazing for us. And yes, it still commutes with SL2, and this is great. Okay. So, but either way, what's happening is you're trying to encode maps from this tensor space to itself by diagrams. These diagrams are maps that commute with the action of the Lie algebra or the Lie group or the quantum group we'll talk about in a second. And the representations of the one are in bijection with the representations of the other, and there's a nice duality pairing transfer of representation theoretic data. Okay. So let's beef this up a little bit. I promised I would talk about braids because everybody's talking about braids. So let's move to the quantum groups. So Lie groups, Lie algebras have very similar representation theory over the complex numbers. Then the quantum groups is a deformation of the Lie algebra. Great. Okay, but most importantly, what it does is it has this fancy operator that if I take the quantum group, just think about it as a deformation of the Lie algebra, and I take the quantum group tensor itself, it has in it this really awesome operator, the R matrix, that gives me a map from the tensor product of two of the modules to the flip that's not an involution. So if I apply it twice, I don't get back where I started. It's not just swap them, it's some isomorphism from V tensor W to W tensor V that's not an involution. The reason to draw it as a crossing is that it actually satisfies braid relations. So this is trying to solve the Yang-Baxter equation, yielded the construction of quantum groups, directly constructing this R matrix. So what this does is it gives me an action of the quantum group on this tensor space, a k-fold tensor product. There's a couple of actions now. Either I can act by the quantum group. The quantum group's a Hopf algebra, so it can act on tensor products. Or I can take these R matrices and apply them to adjacent pairs of these vector spaces, twist, 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 twist. And since V and V are the same, when I twist them, I get back to where I started. And so this is actually an endomorphism on this space built by applying R matrices, twisting things around. And that action commutes with the action of the quantum group on the whole space. Okay. I can also play around with the tensor space. Instead of just taking one representation and taking a k-fold tensor product, what if I throw on some weird representation on the end? So something that's different. Well, that representation has to map to itself. So whatever twisting goes on, I can twist, twist. Whatever twisting goes on, M has to end up back where it started. And so I can draw those as not just braids, but braids with some kind of pole. So that pole, that M, has to go back to itself, but stuff can twist around it. In the middle, it can move to a different place and then move back. And so I get not just braid actions on tensor spaces, but one-pole braid actions on tensor spaces, or two-pole braid actions on tensor spaces, depending on how I want to build my tensor space in the middle. Okay, so we've got some tools. Let's recap about where we are with these centralizer algebras. So we started with the symmetric group. The symmetric group and the general linear group have commuting actions. So I'm starting to build this table where I'm looking at the Lie group or Lie algebra of type A. That's just the general linear group or the special linear group. And I'm looking at the actions on a tensor space that looks like V tensor K. If instead of looking at the type A guy, instead I look at orthogonal or symplectic, and I look at the same shaped tensor space, then I get the Brouwer algebra is the commuting action. And I like the commuting action because I get a pairing between the representations. Fantastic. If I look at small type A, I get the Temporally Liebe algebra. Then we introduce the quantum group. So if I instead act by the quantum group instead of the Lie group or the Lie algebra, I get these braids. And what happens when I pick the same representation over here and look at the what commutes with the action of the type A quantum group on this tensor space? Well, it's going to be some quotient of this braid group, and the quotient is take some quadratic relation on double twists, and what you get is what's called the type A Hecke algebra. So the Hecke algebra appears in lots of different places. Number theorists like it because you want to sum over cosets of some fancy group or whatever. And knot theorists like it because if you take the trace of these operators, you get something like the Jones polynomial. So various knot and link invariants come up when you take the Hecke algebra and you take traces of its elements acting on this space. You get knot and link invariants. Great. If I look at the type B, C, D, so take the orthogonal quantum group or the symplectic quantum group, and I look at something on this space, then it's going to be also a quotient of the braid group. And what you get is the BMW algebra, which also gives you knot and link invariants. I think it's the Homfley polynomial for the BMW algebra. Awesome. These things, they have, okay, so the double twist satisfies some kind of relation. These satisfy Reiter-Meister moves. Okay. If I change up the module that we're acting on, then again I get one pole braids or two pole braids. The corresponding things that if I act on the right spaces, what's the right quotient to be looking at? The affine Hecke algebra of type A, or the affine BMW algebra. If I do two poles, then I get, oh, and the one boundary Temporally Liebe I didn't talk about. Temporally Liebe doesn't care about quantum versus Lie algebra because it's non-crossing diagrams, so there's never over-under crossings anyway. Turns out the Temporally Liebe algebra is the right centralizer for quantum groups and Lie groups, just with different parameters. So those closed loops, you just change what those reduce to. By the way, since I'm the jerk who's using slides, these slides are already uploaded to my website if you want to take a look at them later, since I can't leave anything on the board. Okay, so you start to build these things, changing the module in the middle, changing the type of algebra that you act on. Start to develop a sense that like all of these things were connected. Well, that's not really how it started out. Like for example, if I look at this type BCD picture, really the way it started was, okay, so we had Brouwer dealing with this. We already like in the 30s or something like this. And then if you change up the tensor space in the middle, you get Nazarov in 95 looking at the degenerate affine BMW algebras. That's not what it was called because the affine BMW algebras weren't around yet, but it was taking some UC Murphy elements inside of that thing and pulling them out and making some kind of affine version of this. And sort of implicit in that work is that there was a centralizer relationship. And then pretty soon thereafter, 98 and 04, they started playing with the affine BMW algebras in relationship with the quantum group and started to realize, oh, those have nice knot and link invariants too, with knots in a space with genus 1, okay? And then they said, okay, wait a second. These all kind of have centralizer relationships that are similar. And so with a couple of my co-authors, we said, okay, stop treating these things differently and just pull them all together and treat them like centralizers. Say, okay, the quantum group and the Lie algebra are basically the same, and the tensor space is basically the same. So all these algebras on the other side should basically be the same. And out of that, we get a lot of results. For example, nobody even knew what the center of these algebras were for a long time. They were studying knot and link invariants with these things, and they were studying the structure of them, but they had no idea what the center was. But by looking at the action on this module, we were able to guess what the center had to be and then prove it. You also get things like, with these poles, you get things like if you wrap around the pole a bunch of times and then close it off, you get different kinds of closed loops. And those resolve to various numbers, but you can't just choose any numbers you want. There are lots of trouble with which kinds of numbers can you resolve those loops to. It turns out that this is totally trivial if you think about this as an action on tensor space. And you get intertwiner operators, which are usually associated with Hecke algebras that move you from different basis vectors to other ones, different eigenspaces to other ones. And nobody had any kind of idea about how you would even think about that in these BMW or Brouwer algebras, but it's totally transparent if you think about them as centralizer algebras. So structure of the algebras, different things about the representation theory, and similarities between seemingly different algebras start to bring themselves out if you think about these things in terms of Schur-Weyl duality. Another piece of it, if I go back and I look at this last row instead of the column, you also get similarities arising. So This Temporally Liebe algebra, again, came out of the physics world. And this is this paper that we've been like editing and re-editing for like 3 years now, just because we're trying to get the physicists to be okay with it. And what physicists are we talking about? This algebra was constructed studying Ising models, spin chains, and things like that with generic boundary conditions. Well, if you want to change your boundary conditions, they built this as a two-boundary Temporally Liebe algebra, which turns out to have ties to other Hecke algebras and things like this. And it was kind of implicit in this work that there's probably a centralizer relationship, but it wasn't terribly worked out. But if you look at this link to this affine Hecke algebra of type A and C, and then you think about how did this Temporally Liebe algebra get generalized in the first place, you start to see that actually this belongs in this row. So there should be some kind of space in the middle that looks like V tensor K with two extra modules on either end that look like these two walls. The stuff in the middle is non-crossing diagrams. And if I beef that up from SL2 to the universal thing, that should be braids with two poles. And then what's in the middle? Well, that was this Hecke algebras of type C that were arising. And before this, there was no hint in the world that the other Hecke algebras, not just affine Hecke algebras of type A, but the other Hecke algebras should have some kind of centralizer relationship. And until this moment, trying to study the representations of the affine Hecke algebra of type C was kind of hard. They did a lot of really fancy geometry, nilpotent cones and things like that, just to try to construct some of the representations, some of the special representations of this Hecke algebra. If we can put it in the centralizer framework, all of a sudden you get lots of representations of the affine Hecke algebra that have nothing to do with geometry, that are just, I take representations of some quantum group, they're in duality with representations of this Hecke algebra. Okay, so let's see this happen.
What quantum group is that?
This is the type A, well, okay, so this is all of the quantum groups, right? Okay. The universal object is the two-pole braids. Universal means whatever quantum group you want, whatever space you want. But if the quantum group is of type SL2, and the space is special, then the corresponding quotient of the space is the two-boundary Temporally Liebe algebra.
Wait, what's the one over?
The one over is generic type A. So GLN, type GLN, type SLN. So not just SL2 and GL2, but SLN and GLN. So let's watch it happen. Let's see what is this affine Hecke algebra of type C anyway, and why should it have anything to do with two-pole braids? So here's the affine Hecke algebra of type C. I've seen some Dinkin diagrams in some of these talks, but basically this is a code for generators and relations. So if I'm giving you an algebra, the nicest way I can give it to you is either a picture or with generators and relations. So this algebra, whatever it is, it's generated by k plus 1 things, indexed by 0, 1, 2, 3, up to k. The relations are given by this picture saying that two generators have relations according to how they're connected. 2 strands, 1 strand, or no strands. So if they have no strands between them, then it satisfies the relation Ti, Tj equals Tj, Ti. If they have 1 strand between them, they satisfy the relation Ti, Tj, Ti, because 1 strand means 3. So Iji is Jij. That's the braid relation. If it has 2 strands between them, then I have 4, so I want a length 4 braid relation. So Ij is Ji. Okay. And then the last thing to make it a Hecke algebra, not just make it a braid group. So up till now, that's the two-boundary braid group. And you'll see why in a second. But if I want to make it the Hecke algebra, I have to quotient out by these quadratic relations. If I twist twice, that's the same thing as a linear combination of twist once and a constant. So that's the Hecke algebra. Now why do these braid relations correspond to this picture? Well, let's look. So you've already maybe seen the braid relation being, 1, 2, 1 is 2, 1, 2. So I'm going to identify these generators with some pictures. So the stuff in the middle, 1, 2, 3, 4, up to k minus 1, is all going to be drawn by these adjacent twists. Go to the ith strand and twist it with the one right next to it. For k and for 0, these endpoint ones, they're going to be wrapped around a pole. So for the two-pole braid group, I've got poles on the ends and braids in the middle. So the kth one is go to the pole on the right and twist around it. The 0th one, go to the pole on the left and twist around it. So if I take stuff in the middle, so I is between 1 and k minus 2. If I do I plus 1i, that's twist, twist, twist. That's the same thing as twist the second one, the first one, and the second one, because you can take this middle strand here and pull it off to the right, or to pull it off to the left. The pole wrapping, though, says that, okay, if I twist and then wrap, and then twist and then wrap, that should be the same thing as wrap, twist, wrap, twist. And how do I do that? I take this strand here, I pull it off to the side and pass that one and pull it down, and that's what I've got here. Okay, so that's a length 4 braid relation. Same thing happens on the other side. So in fact, the braid group associated with this Dynkin diagram is the 2-pole braid group. And then when I take quotients by the Hecke relations, that's just saying, okay, if I twist twice, that's a linear combination. Okie doke. So what happens? For any complex reductive Lie algebra, you've got a nice action on this tensor space just by our matrices. It's not necessarily everything that I could do, but it's a nice action on that space. And it commutes with the action of the braid group. It commutes with the action of the quantum group. When I take G as GLN and I take nice choices of M, N, and V, that action factors, the action of the 2-boundary braid group factors to an action of the Hecke algebra. Which means if I look at the quotient of the action, I get the Hecke algebra. And what do I get out of this? For free, all of a sudden I get a whole bunch of beautiful combinatorial results because I have all this beautiful combinatorial representation theory for the quantum group. So again, I'm just going to take the type A quantum group, its representations, indexed by partitions. I know how its representation theory works as far as taking k-fold tensor products of n-dimensional space. That's that first lattice that I showed you, build up with partitions. M and N, what I need is very special partitions that give me quadratic relations. Turns out I need big rectangular partitions. And this space builds up to a very beautiful lattice. Has lots of nice, beautiful type C symmetry to it that you wouldn't have expected necessarily otherwise until I told you, oh, there's a type C Hecke algebra hanging out. Oh yeah, of course there's going to be type C symmetry. So I get combinatorial classification and construction of irreducible representations of the Hecke algebra, which before were very difficult to get at, unless you said very specific things about the parameters or you did special stuff with geometry. I have to put down geometry. It's just, it was a huge construction to get at those representations. You also get a diagrammatic intuition for the Hecke algebra. If you look at these papers where they're trying to do calculations with this algebra, there are these huge, long calculations with generators and relations. Swap this braid relation for that braid relation. Swap this braid relation for that braid relation. There are indices that are like, the index is 5 pages long where they're just trying to do a calculation. And instead now you can just draw the Hecke algebra using braids. Beautiful diagrammatic computations. And then you get a classification of the representations of the Temporally Liebe algebra. Remember, that was where the physicists started, with SL2 or GL2 instead of SLN and GLN. You squash that down, you get a quotient that's the 2-boundary Temporally Liebe algebra. And now we can get at it not just by looking at transfer matrices in these diagrams, but you get this classification of representations of the Hecke algebra. You say, okay, which one's factor through the Temporally Liebe quotient? And now you've got a classification of the representations of the Temporally Liebe algebra. For free. Okay, so mostly what I've been getting at, if you take one thing away from this talk, it's that Schur-Weyl duality provides a beautiful framework for connecting algebras that show up all over the place in the wild. Things that are coming from physics, things that are coming from knot theory, things that are coming from number theory, things that are coming from quantum groups, Lie algebras, Lie theory, topological spaces, looking at tangent planes and things like this. And in fact, this is just a very small piece of the picture. So not just Lie algebras and quantum groups, but you can look at Lianes, which are a different deformation. And you can look at other sorts of tensor spaces in the middle with other sorts of braid actions. But usually what you get is a pairing between a classical algebra of some sort and the action of some diagrams. All right, I'll quit there.
Any questions for Zajj?
Yeah.
Can you make 3 poles work?
Yeah, so as you modify the tensor space, you can get lots of different kinds of shapes of the braid group. So his question was, can you make 3 poles work? And in fact, One of the projects we're working on is looking at double affine Hecke algebras. So double affine Hecke algebras were a pretty big deal recently, looking at things having to do with various kinds of symmetric polynomials. So McDonald polynomials arise when looking at double affine Hecke algebras. And it turns out that if you want to study these things, the place you want to start is the three-pole braid group. And various quotients of the three-pole braid group give you various double affine Hecke algebras. But the wonderful thing about the three-pole braid group is that if you look at those poles and you treat those three poles as sort of similar poles, there's an action of S3 on that space, permuting the poles. You can conjugate by S3. And that action will actually give you a connection to modular forms in kind of a special way. And so the three-pole braid group is very special. It's not just like, okay, 1, 2, 3, 4, 15 poles. Three-pole braid group, some very awesome stuff happens.
Well, I guess, like, can you draw, so for the two poles you drew a Dynkin diagram, and the two poles, you could see the two poles on the Dynkin diagram.
Yeah.
Could you draw a Dynkin diagram here for three poles, and you could see the three poles in the Dynkin diagram?
Usually what we do with the three poles is that we draw, even with two poles, a lot of the time what I do is I like to bring the pole over to the side, like so the two poles are on the side, and what you draw is two Dynkin diagrams. You draw three Dynkin diagrams.
You draw?
I mean, it's the three type A Dynkin diagrams is all. So what I was saying is the two-pole braid group, you start out with something like this. But in fact, usually I want to bring the two poles over to the side, and so I deal with it by drawing two Dynkin diagrams and dealing with the two poles separately, and then saying I've got some relationship between the two twists around the poles. So it's not a single Dynkin diagram.
Dynkin diagram type C.
Yeah, affine type C, yeah.
Okay.
And those are two affine type A's, or affine type GLN, or type B. Yeah, the affine type GLN braid group is the same thing as the finite type B braid group.